Explanation: when we write a program that breaks a big problem into many smaller pieces, we often get a formula that tells us how long the whole job will take. This formula is called a recurrence. Imagine you have a huge chocolate bar and you keep snapping it in half until each piece is small enough to eat. To know how long it will take you to finish, you could count every snap one by one. That would be slow and messy. The Master Theorem is like a magic shortcut that instantly tells you the overall time just by looking at three numbers in the recurrence. It is needed because many important algorithms such as sorting, multiplying numbers, and multiplying matrices use the divide and conquer idea, and solving their recurrences by hand each time would be a huge waste of effort. The Master Theorem works for recurrences of the form T of n equals a times T of n over b plus f of n, where a greater than or equal to 1 is the number of sub-problems created. B greater than 1 tells how much smaller each sub-problem is, and f of n is the work done outside the recursive calls, like the time to split the problem and combine the answers. Define n raised to the log base b of a as the critical exponent that represents the total amount of work done by the recursive calls alone. The theorem has three cases. Case 1, f smaller. If f of n is big O of n raised to log base b of a minus epsilon for some epsilon greater than 0, then the recursive part dominates and T of n is theta of n raised to log base b of a. Case 2, f matches. If f of n is theta of n raised to log base b of a times log to the k of n for some constant k greater than or equal to 0, then both parts contribute equally and T of n is theta of n raised to log base b of a times log to the k plus 1 of n. Case 3, f larger. If f of n is omega of n raised to log base b of a plus epsilon for some epsilon greater than 0, and the regularity condition a times f of n over b is less than or equal to c times f of n holds for some constant c less than 1 and sufficiently large n, then the outside work dominates, and T of n is theta of f of. Explanation: to use the theorem, you first have to read the recurrence and pull out the three ingredients. R is how many times the function calls itself. In the recurrence T of n equals 2t of n divided by 2 plus n, the term 2t of n divided by 2 means the function calls itself twice, so a equals 2. B is what you divide the input size by in each call. The same example uses n divided by 2, so b equals 2. F of n is everything that is not a recursive call. In the example, the extra work is the linear term n, so f of n equals n. Another example, T of n equals 3t of n divided by 4 plus n squared. Here we have a equals 3 subproblems, b equals 4, each subproblem is a quarter of the original size, and f of n equals n squared, the work done after the three calls. Once you have a b and f of n, you can plug them into the three cases of the Master Theorem. A helpful analogy is a bakery that makes loaves of bread. The bakery decides to split each loaf into a smaller pieces, each of size 1 over b of the original. The time to cut the loaf is f of n by looking at a b, and f of n we can predict the total baking time without actually baking every loaf. Explanation: after you have a b and f of n, the next step is to compare f of n with the expression n to the power of log base b of a. This expression tells us how much work the recursive calls would do if there were no extra work. Compute log base b of a, for example. If a equals 4 and b equals 2, then log base 2 of 4 equals 2, so the critical term is n squared. Look at the growth of f of n. Is it slower than n to the power of log base b of a? Is it about the same, or does it grow faster? Think of a foot race. N to the power of log base b of a is one runner and f of n is another. If f of n runs slower, case 1, the first runner decides the finish time. If they run side by side, case 2, the finish time is a little longer because they have to stay together. If f of n sprints ahead, case 3, then f of n determines the finish. Mathematically, you check the three relationships. Case 1, f of n is big O of n to the power of log base b of a minus epsilon, for some epsilon greater than 0. Case 2, f of n is theta of n to the power of log base b of a times log to the k of n, for a constant k greater than or equal to 0. Case 3, f of n is omega of n to the power of log base b of a plus epsilon, for some epsilon greater than 0. Once you know which relationship holds, the theorem tells you which term, the recursive part or the extra work, dominates the total running time. Case 3 of the Master Theorem has an extra requirement called the regularity condition. It makes sure that the extra work f of n does not shrink too quickly when the problem gets smaller. Formally, we need a constant c less than 1, and a size n sub 0 such that for all n greater than or equal to n sub 0, a f of open fraction n divided by b close is less than or equal to c f of n. If this inequality holds, the large f of n truly dominates, and the theorem gives t of n equals theta of f of n. Example, t of n equals 2t of open n divided by 2 close plus n squared. Here a equals 2, b equals 2, f of n equals n squared, and n to the log base b of a equals n to the log base 2 of 2 equals n. Since f of n equals n squared grows faster than n, we are in case 3. Check regularity. A f of open n divided by b close equals 2 times open n divided by 2 close squared equals 2 times n squared divided by 4 equals n squared divided by 2. We can pick c equals 1/2, which is less than 1, and see that n squared divided by 2 is less than or equal to 1/2 times n squared holds for all n. Thus the condition is satisfied and t of n equals theta of n squared. Edge cases arise when f of n is very close to n to the log base b of a but not an exact power. For example, f of n equals n to the log base b of a times log n. The basic Master Theorem does not cover such forms, and we either fall back to a more general version called the extended Master Theorem or use other tools like the Acra-Bazzi method. A simple analogy. Imagine a garden hose which represents the recursive work feeding water to a plant, while a bucket representing the extra work is poured directly onto the plant. The regularity condition says the bucket's contribution must stay big enough even when you look at smaller sections of the garden. Otherwise, the hose might still be the main source of water. Explanation: let's see the Master Theorem in action with 3 famous algorithms. 1. Merge sort. Recurrence: t of n equals 2t of n over 2 plus theta of n. Here equals 2, b equals 2. F of n equals theta of n, and n to the log base b of a equals n to the log base 2 of 2 equals n. Because f of n equals theta of n to the log base b of a, case 2 with k equals 0. T of n equals theta of n log n. So merge sort runs in n log n time. 2. Karatsuba multiplication, fast integer multiplication. Recurrence: t of n equals 3t of n over 2 plus theta of n. A equals 3, b equals 2, f of n equals theta of n. Compute n to the log base b of a equals n to the log base 2 of 3 approximately n to the 1.585. Since f of n is big O of n to the 1.585 minus epsilon for epsilon approximately 0.585, we are in case 1. Therefore t of n equals theta of n to the log base 2 of 3 approximately theta of n to the 1.585. This beats the ordinary big O of n squared multiplication. 3. Strassen's matrix multiplication. Recurrence: t of n equals 7t of n over 2 plus theta of n squared. A equals 7, b equals 2, f of n equals theta of n squared. Critical term n to the log base 2 of 7 approximately n to the 2.807. Because f of n is big O of n to the 2.807 minus epsilon, case 1. T of n equals theta of n to the log base 2 of 7 approximately theta of n to the 2.807. This is faster than the naive big O of n cubed matrix multiplication. In each case, we only needed to read the 3 numbers a, b, f of n, compare f of n to the log base b of a, and pick the right case. No long induction or guessing required. The Master Theorem does the heavy lifting for us. The Master Theorem is powerful, but it does not work for every recurrence. Limitations: it only handles recurrences where the subproblem size is exactly n over b, and the number of subproblems is a constant a if the split is uneven. For example, t of n equals t of n over 2 plus t of n over 3 plus n. Or if f of n contains unusual terms like n to the log base b of a times log n, the basic theorem cannot be applied. Extensions: the extended Master Theorem allows polylogarithmic factors in f of n, the log to the k of n part in case 2. For more general forms, the Acra-Bazzi method works. It solves recurrences of the shape t of x equals the sum from I equals 1 to k of a sub I times t of b sub I times x plus g of x. where the b sub I can be different and g of x can be any reasonably nice function. The solution involves finding a number p that satisfies the sum of a sub I times b sub I to the p equals 1, and then using an integral of g of x weighted by x to the p. When to use alternatives? If you try to plug a recurrence into the Master Theorem and find that f of n is not polynomially related to n to the log base b of a, or the regularity condition fails, switch to acrobacy or to the recursion tree method. These methods are a bit more work, but they guarantee a correct bound. Think of the Master Theorem as a fast food restaurant. It serves a limited menu, standard recurrences, quickly. When you need a fancy dish, irregular splits, or weird f of n, you go to a full-service restaurant, acrobacy, that can handle any order, though you may have to wait longer. In practice, most textbook algorithms fit the Master Theorem, so you use it first. If it doesn't fit, you know the backup plan.